Today we discuss section 18, continuity of complex functions. This is the definition. A function f is continuous at a point z0 if all three following conditions are satisfied. The first condition is limit z tends to z0, f of z exists. Second condition, f of z0 exists. Finally, those two quantities should be equal. Limit z tends to z0, f of z equal to f of z0. This is f of z0. If these three conditions are true, then we can say that f is continuous at the point the complex number is equal to z0. So this is analogous to the definition of the continuous function of real analysis. And classically we can define, this is another definition or equivalent definitions for this. We already discussed the definition of the existence of limit. So we apply that definition to the third condition. We will get for every epsilon greater than 0 there should exist delta greater than 0 such that modulus f of z minus f of z0. We just replace those limit capital L or that limit quantity by the functional value itself is less than epsilon whenever mod z minus z0 less than delta. So what is the geometrical meaning of this? We already discussed that we cannot get the graph of complex functions as it is reside in the four-dimensional space, so that is not possible to draw the graph of this, but we can use two complex planes to discuss complex functions. We call it as one as xy plane and next is uv plane. So these are two planes to discuss function f. So this f is a function from one complex plane to another. If we fix a point z0 here in order to find the definition of or continuity of f at z0, we need to consider f of z0 here. Okay, so this is what we call omega naught, that is equal to f of z0. And what is the meaning of this epsilon delta definition? If we consider any epsilon neighborhood of or epsilon disk about this omega naught or f of z0, corresponding to this epsilon disk, we need to get a disk at z0 at the with the radius of delta. Okay, so corresponding to every epsilon disk here, there should exist a delta disk at about this z0, such that image of every element of this delta disk should be contained in here. This need not be mapped to this epsilon neighborhood of omega naught, but every image of this will be contained in this disk. So this is the definition of the geometrical meaning of this epsilon delta definition of the continuity. Okay, so if we define complex function, still we can use them. We can make use of this complex planes, two complex planes to discuss this f, or geometrically we can represent the continuity of this f in this manner. Okay, so there are a number of theorems we have proved in the last sessions involving the limit of a function. So those results can be carried out. We can use the same theorems here by replacing those limit capital L by our function value of f of z at z equal to z0. Okay, so the sum rule of limit can be extended to the sum rule of sum rule of continuity. Similarly, the product rule of limit can be extended to the product rule of continuity and the quotient rule as well, provided the denominator is non-zero. And next we will prove another theorem for this continuity. That is theorem 1 in this section. Theorem 1, that is the continuity of composition of two functions. Continuity of compositions of two functions. Compositions of two continuous functions. Okay, this theorem says that composition of two continuous functions is itself a continuous function. Okay. Composition, this can be treated as title, composition of the composition of two continuous functions. Composition of continuous functions. This itself is itself continuous. Okay, so we start with two functions, two complex functions, and we compose each other, and we will consider the continuity of the resultant function. Okay, for that we need to consider, in order to consider the composition or complex functions, we consider complex plane like this. First of all, we have xy plane. This is xy plane, that is the x, we can take x along this way and y this way, and in order to discuss the another, I take the domain of f is this. Okay, and from this you can define f of z. F of z is from xy plane to uv plane. So we consider this image plane as omega plane. So this is the omega plane, and this is the codomain of f. So this, if f is equal to u plus iv, we consider this as uv plane. Okay, and in this case we will consider one more plane to discuss g. If this g is defined from uv plane to another plane, another complex plane, we call this as g of z, and the components of g as capital U plus capital V, then we can call this plane as uv plane, capital uv plane. Okay, so this is a function from f is a function from xy plane to uv plane, and g is a function from small uv plane to capital uv plane. Okay, if this is the case, if you fix a point z0 here, we can get an image of this z0 at this point. Okay, say f of z0, and corresponding to this f of z0, you will get a point g of f of z0, g of f of z0 in capital uv plane. Because f of z0, if you apply g on the f of z0, you will get another point in capital uv plane. Okay, so what you have to prove is, if you compose this g and f as a g composition f. Okay, so we call it as some capital W, and we can consider this as the function of the form g of f of z. We need to prove that this is a continuous function. In fact, this is a function from the domain of f to codomain of g. Okay, so this is, in fact, this function is from this composition, g composition f is a function from xy plane to capital uv plane. Okay, that is xy plane to uv plane. So this is the domain and codomain of the composition. So we have to prove that g composition f is continuous at z0. Yeah, so in order to prove this g composition f is continuous at z0, we need to consider a epsilon disk about g of f of z0. Okay, so if we have a epsilon disk here, corresponding to this epsilon, since this is a function from uv plane to capital small uv plane to capital uv plane, so corresponding to this f of g of f of z0, if we take any epsilon neighborhood here, the corresponding to this neighborhood, there exists a gamma neighborhood here, because we know that g is continuous at f of z0. Okay, f is continuous at z0, g is continuous at f of z0, then we will prove that g composition f is continuous at z0 itself. Okay, so corresponding to this epsilon neighborhood or disk, there exists a gamma disk, gamma or delta disk. Okay, so using the definition of continuity of g at f of z0. Okay, we have for epsilon greater than 0, there exists a gamma greater than 0 such that modulus of g of f of z minus g of f of z0 is less than gamma. You can make, less than epsilon. You can make this is less than epsilon whenever mod f of z minus f of z0 less than delta. sorry, less than gamma. Okay, less than, we write it as less than gamma. This is mod f of z minus f of z naught less than gamma. So corresponding to epsilon, there exists a gamma greater than 0. Now you take this gamma corresponding to gamma greater than 0. That means if you consider this neighborhood of f of z naught, there exists, since the being f is continuous at z naught, corresponding to this gamma neighborhood, there exists a delta neighborhood here. Okay, there exists a delta neighborhood here, such that image of every element of this neighborhood should be contained in this. Okay, so corresponding to this gamma greater than 0, there exists delta greater than 0. This is because of continuity of f. F is continuous. Since f is continuous, you can get this delta, such that modulus of f of z minus f of z naught less than this gamma whenever mod z minus z naught less than delta. Okay, so whenever an z belongs to this disk, then the image should be in this disk. Okay, in fact, what we have written here is whenever epsilon greater than 0 and gamma greater than 0 epsilon greater than 0, there exists a gamma greater than 0, such that g of any omega or any w, g of w minus g of if we call this f of z naught is equal to w naught, we have g of w minus g of w naught is less than 0. Okay, so this is true for in fact this f of z naught is denoted by this w naught. Then this w is an arbitrary element of this neighborhood. Okay, that means this is w minus f of z naught less than gamma. So whenever a w satisfies this condition, that means whenever a w belongs to this disk, then we can say that the distance between f of z naught and w is less than gamma. For that w, we have this result. Okay, now you consider this one. Whenever z minus z naught less than delta, f of z minus f of z naught is less than gamma. So you can write this f of z as a w which satisfies this condition. That's why I have written like this. Okay, so by the definition of continuity of g at f of z naught says that this result is true for every w irrespective of that w is f of z or not. Okay, so this is true for every w satisfying this condition. Okay, so in fact, in order to prove this result, we will take f of z for which the distance between f of z and f of z naught is less than gamma. Okay, so we start with this. Whenever mod z minus z naught less than delta implies, so corresponding to this epsilon greater than 0, we can get this delta. So whenever mod z minus z naught less than delta, we will get f of z minus f of z naught less than gamma. Okay, this implies from this, whenever this distance is less than gamma, we will get this g of f of z minus g of f of z naught is less than epsilon. Okay, so for every epsilon greater than 0, there exists a delta greater than 0, such that this implies this is less than epsilon. This proves the continuity of G composition f at z naught. Okay, so G composition f is continuous at z equal to z naught. So this proves the first theorem of this section. Next we will discuss theorem 2. That the statement of theorem is if a function f of z is continuous and non-zero at a point is not, then f of z not equal to 0 throughout some neighborhood of that point. Okay, so that will be used to prove another theorems the following sessions. To prove this the definition, if a function f of z is continuous and non-zero at a point z0, that is f of, for the proof we can write f of z0 is not equal to 0. Therefore, we can get f of z0, modulus of f of z is always greater than 0. This is a fixed quantity greater than 0. If this happens and f is continuous, then you can find a neighborhood or a disk in which this f of z is throughout non-zero. Okay? So if this f of z0 is not equal to 0, if this is not equal to 0, then you can easily find a disk about this f of z0, at which if you take any z, then you will get f of z is always not equal to 0. That means there should exist at least one neighborhood or at least one disk with this property. Okay. If f is non-zero at one point, then not even at one point, you can still find a disk that contains uncountable number of points, uncountable number of complex numbers, at which this f takes the non-zero values. Okay, so this is the definition of, this is the statement of next theorem 2. This is analogous to the condition that this is also true for real functions. If whenever a real function attains a value, a non-zero value at some x0, if this is x0 and at this point x0, the function attains, if this is x0 any real number, and if f of x0 is non-zero, then you can still find a neighborhood of f of x0 in which this f is non-zero everywhere. Okay, so similarly we will prove the same result here. F of z0 is non-zero implies f of z is non-zero in a neighborhood or a disk, every point of that disk. So we use the continuity of this f to prove this, and whenever we assume this is non-zero, then this is a positive quantity. This is a fixed positive quantity. Since this z0 is fixed, as far as z0 is concerned, this quantity is fixed. Okay, and put epsilon, which is equal to modulus of f of z0 by 2, since this is positive and this is also positive. So corresponding to this positive quantity, this epsilon, using the continuity of f, there exists a delta greater than 0 such that modulus of f of z minus f of z0 less than epsilon. What is epsilon? Epsilon is modulus of f of z0 by 2. Okay, whenever mod z minus z0 less than delta. Okay, since this is the epsilon, then corresponding to this epsilon, there exists a delta such that modulus of this quantity is less than epsilon. Since this epsilon is this quantity by 2, then we can replace those things here. Okay, so this should be true for every z satisfying or z lies on this disk. Okay, so this implies that now we have to prove, we will prove that our claim is for every z satisfying this. Okay, what is the meaning of that? At z equal to z0, you can get a disk with radius delta. Okay, if you take any z here, we will prove that f of z is non-zero. Okay, because if we consider this delta disk or delta neighborhood about this z0, then you can consider f of z. Whenever f of z equal to 0, or if f of z equal to 0, for z such that mod z minus z0 less than delta. So this is our candidate. Okay, this disk is our candidate. So if we take any z from this disk, if this f of z equal to 0, then this statement. Okay, if you consider the statement, this statement implies that, okay, f of z minus f of z0 less than epsilon, which is equal to modulus of f of z0 by 2 implies, this implies, put f of z equal to 0 here, you will get mod f of z0 is less than mod f of z0 by 2, which is a contradiction. Okay, since this is a non-zero quantity, non-negative or positive quantity, so that positive quantity is less than its half. Okay, so this is a contradiction. So we can say that f of z never be zero. F of z never be zero. This equal to zero is not possible in this disk. Okay, never be zero for all z such that mod z minus z naught less than delta. Okay, so this proves theorem 2. Okay. Now we have some definitions. We already discussed these definitions in your assignments. That is, one is definition of closed set, region set to be closed. So please remember these things. Closed region. So please refer your assignments for the same. Okay, closed region R, and after that the textbook bounded function. We already discussed what is bounded function in the assignment. Bounded function or bounded region. Okay, bounded region. Here we have discussed bounded region. Bounded region means if it lies inside some disk, some circle or disk centered at origin. The meaning of boundedness is if you consider any set here, any region here, and if you can enclose this region in a circle of radius, some radius r, if you can enclose this in a circle of radius r, then you can say that this region is bounded. Okay. So if you consider any region in the plane, and if you can enclose that region in a circle with radius, some radius r, then you can consider that region as this bounded region. Okay, so this is the definition for bounded region and closed region. Closed region means that the complement is open, or you can say that that is a region consisting of all the points of region and as well as the boundary points. So we have already discussed what is the closed region and open region in the assignments. Okay, next we have theorem 3. This is the statement of theorem 3. If a function f is continuous throughout a region R, that is both closed and bounded, there exists a non-negative real number capital M such that mod f of z is less than or equal to M. That means this is the definition of the boundedness of a function. F is bounded means mod f of z is less than or equal to M. So if the region is bounded and closed, then the function is itself bounded. That is the meaning of this statement. Okay, and the equality holds for some z in that R, not z that R. Okay, so we prove this theorem using the real function. We take f of z as u plus iv, okay, u of xy plus iv of xy. Then f mod f of z means this is equal to square root of this u square, u of xy square plus v of xy square. So this is u square plus v square, and this u and v are real functions. Okay, this u is a function from r cross r to r, and v is a function from again r cross r to r. Okay, so these are two functions. So this f is continuous means f is continuous if and only if u and v are continuous. We already proved this. This is for limit of functions. F has a limit at z equal to z naught, then u and v have the limit at the same the corresponding point x naught comma y naught. Okay, so if you replace those limit by the corresponding functional value, you will get the equivalency of this, the continuity of f and continuity of u and v. Okay, so if f is continuous, then we can then u and v are continuous. Okay, now we can say that since u and v are continuous, then u square plus v square is continuous, and the corresponding square root. We know that root x square is always continuous, so root of a real function is always continuous. Okay, so this is a continuous function, is a continuous function defined on closed sets. So a continuous function defined on a closed set of R2 or R plus R or R that attains the maximum value. Okay, that means this u of root u square plus v square is always less than or equal to some m. Okay, this is because of the real function. Real function defined on a closed set is always bounded and attains the maximum values. Okay, so and we have there exists some x comma y such that x comma y belongs to that region such that root u square xy plus v square xy equal to that m. Okay, so using these two conditions, from this you can say that this is the modulus of f of z. So modulus of f of z is always less than or equal to m, and from this you can say that modulus of f of z equal to that m. Okay, or not only the modulus, the corresponding function value at this point that f of z attains that point. So equality holds for some z belongs to those region R. Okay, so this is the consequence of real functions to get the boundedness of the continuous function defined on a closed and bounded region. Okay, with this we can conclude section 18. The next class we will discuss section 19 that deals with derivatives of complex functions.